Hello and welcome to VitoshAcademy. Today we will learn about XGBoost, a Python library for machine learning that stands for Extreme Gradient Boosting. This is its documentation that you see here. And of course, we will use it, the documentation, the library, and we will create a hands-on with a Jupyter notebook with a small CSV that explains every step of the process in really simple and plain language. So let's go back to the naming. XGBoost, what does it mean? X comes for extreme. So the idea there is that the library is really quick and it is accurate, it is speedy, it scales up on big machines. Gradient means that the library actually follows the direction that reduces the error the fastest. Think of it as an error hill. The gradient points downhill, so each new tree actually is a small step that lowers the loss quickly. And boosting, we add small decision trees, one after the other. Each new tree looks at the rows of the earlier tree and it decides what was wrong and then corrects the part of these mistakes. At the end, we sum the contributions from all trees to make the final prediction. So far so good. Let's take a look here and then we'll go to Jupyter Notebook and we'll start programming. So here on the official documentation, we have a simple example of a classification and regression trees. And pretty much it classifies whether someone will like a hypothetical computer game X. So how does it function? Tree 1, actually here, it asks, is the person with less than 20 years old of age? If the answer is yes, then you go to the left leaf here and you add +2 to the running total. If the answer is no, you go to the right leaf and add -1. So then we go to the second tree and the tree asks, do you use computer daily? If the answer is yes, it adds +0.9. If it is no, it removes 0.9 from the score. So pretty much these leaf numbers are the scores. So you have to add them up. You see for the young boy, it is 2.9, and for the old fellow, it is -1.9. So this one, for the young boy, it is a strong push towards the positive class, and for the old fellow, it is a strong push towards the negative class. Just in this example, you see some interesting idea of why two trees are actually possible. You see this lady here, she's over 20, but she uses computer daily, so she's somewhere in the middle on the prediction whether she would like a specific computer game. So in real models, we have multiple small trees. Each one is simple, but together they capture the patterns that a single tree would miss. So let's go to Jupyter Notebook and see what we can do there. So we are in Jupyter Lab actually, not in Jupyter Notebook, because I'm using Jupyter Lab now. And here I'm having already 3 cells that are pre-written for me and for you. And I'm just pressing Shift and Enter. And with the first cells, we are loading the libraries NumPy, Pandas, Matplotlib, XGBoost, and sklearn, pretty much with few alias. So coming here and pressing Shift and Enter twice more. And for the data frame, I have prepared one file, Churn, but it's obviously saying that there is no such file or directory. So what should we do? Okay, I mean, I know the answer is a CSV, so we should go with churn.csv. The idea here is that whenever you see this kind of screen in Jupyter Notebook or in Jupyter Lab, don't worry about it, just try to see, okay, what's going on? Is it something normal? Most probably it is. If it is not, then yeah, just try to debug. Okay, so what can we do? Let's take a look at what we have in the DF. pretty much we can say df shape, which would give us something. And df shape actually has 14,000 rows and 8 columns, which is something what we do, what we should know about it is pretty much their names. As you see, they are starting with 0, so they should finish with 7 because they are totally 8. And they are called tenure months, monthly spend, support calls, promo, eligible, debt ratio, age, is international, and then we have the churn, which is pretty much the result of this. And what we're going to do is we're going to try to educate with XGBoost our model to predict what the result would be, what the churn result would be, so to say. Info, we have a lot of not new, but as you see, they're different. So it would mean that we have a lot of no's. For example, here, our no should be that much, 287 no values. Okay. And they wouldn't be new, but they would be not a number. This is how we do it. Missing values are generally fine. XGBoost learns a default branch for not a number pretty much at each script. Let's see what else we can do. We can say df head just to see how our data looks. And of course we get 5. We can change it to df head 7 and we're gonna have 7 entries. And we see that someone with 32 tenure months who spend on our website something like this per month get 8 support calls. Yeah, with good debt ratio, I guess 21 years old, is international. This means true. Yeah, we're gonna lose him because of the support calls, I guess, or something else. But with the others, with 0 support calls, it's kind of obvious that we are not losing them. Okay, we have 14,000 rows to the site, and this is just an example. What else can we do in order to see our database? We can say df describe, and in order to get it nicely, we can transpose it. So tenure months, pretty much the count is this one. It should be 14,000, but some of them are empty. We have the mean, we have the standard deviation, we have the minimum, the 25%, the 50%, the 75%, and we have the maximum. Here is how you find out that churn is a binary value, the one that we are going to predict. And we can see that somewhere around 57, the 75%, we are starting to see people with churn. Okay, so far so good. Let's take a look and see how many exactly the churns are. So what we can do is we can say df churn. If we just do this, nothing would happen. But if you do this, we would get pretty much an idea of what's going on in the churn column, but we are not going to use it. We want to say value counts. And let's see. So we have like 8,000 churns with 0, and we have 5,000 churns in our data with 1, which is good. I mean, it means we have both positive churn and negative churn, so we can kind of learn. Let's normalize this. And let's rename it. Just to share. I mean, we are not going to rename the columns. We are just going to rename it here, so it looks better on Jupyter Lab. So 59, almost 60% of the data is with 0 churn, and about 40% is with positive churn. This is an interesting way to present data once you have it. Immediately seeing, okay, value counts, and then normalize true. This is how it works. And now let's start nicely working with our tool and with our XGBoost. So let's start splitting the data fairly. We see here X and Y. I have prepared already for you. And X will drop the churn column because otherwise it would be a bit unfair trying to predict the churn based on its own column. And Y, or Y in English, would be the churn itself. So Shift and Enter. Let's see what we got. X looks like this. Just curious if I use small x. Nope, doesn't work. X, the big one, we have everything but the churn. And in Y, we would have only the churn. Okay. To this, delete the cell. So first cut, 80-20% train versus test. And it looks like this. Pretty much, if you take a look here, we just got it filled up with something. TE starts for test, TR starts for train, Y test and Y train. This is pretty much how we split it. So 2800 are the test and 11,200 are the train, altogether making 14,000, which was the sum of our data. Okay, fair enough. This is how we do it, the first cut. And the second cut, we do pretty much the same with one exception. We make a second cut pretty much saying, hey, we're gonna split it actually into 60% train, 20% validation, and 20% test. So we do it, and now the XTR is already something new. 84,000 X validation, 28,000, and X test is 28,000. So X test, yeah, makes sense. That's good. What can we do now? Further, we can take a look how many non-churns are in train, because if we only train on churn, it would be a mistake. So we'll call them negative, and it would be looking like this. Something like this. Let's see how many negative. 5,000. Quite okay. Let's get the positive as well. So whenever it is equal to 1, just sum them. Negative, I'm just curious, positive. Okay, so negative and positive should be 8,400 or 8,400, which is good. And let's put something new, which is called scale positional weight. So to say, it simply tells us that it's scale positive weight, actually. That's whether the positives are more or the negatives are more. And it's really simple. It should be like this. SPW equals negative divided by max, positive and 1. Yeah, 149, which is good, I guess. In our case, they're okay. You're probably wondering, what does this mean? Stratify. And the answer is that this stratify actually makes sure that pretty much it keeps the churn ratio similar in each piece, so to say. See here the Y, the churn ratio, It is really, really quite well developed. I mean, you shouldn't be the one saying, okay, we should have so many y's like positive, so many negative. No, this magic here, Stratify, does the whole thing for you. Let's write this down somehow. We can print it. So we'll say train validation test. They would be the following: x tr shape, x va shape, and then x te shape. Yeah, works. So 84, 28, 28. Yeah, fair enough. And additionally, we'll print also the negative, the positive, and the SPW, scale, positive weight. So we can do it nicely, saying if and then negative neg, then positive pos, and then scale positive weight, and it would be something like round SPW up to the first one, because I don't want to see them all. And would it work? Of course not. It wouldn't work because it feels it has forgotten something. Just thinking, round SPW. Let's try like this. Okay, it works. So SPW equals, okay, I remove this. Yeah, something like this. And I don't know why I left it like that, but okay. Scale positive weight of 1.5. And that's pretty much okay so far. Let's continue with preparing the metrics objects. So let's wrap the data for the fast training. Pretty much the metrics, the one that we are using here, it's a class, and it's the XGBoost internal fast format. It makes training and predicting actually really efficient. And we pass the feature names, so it is usable later. For labels, let's see what we have here. Feature names, we have tenure months, and the other 1, 2, 3, 4, 5, 6, totally 7 names. And what we have here, DVA, oh, we have the nice class. Okay, so we are finally here. Let's train a baseline XGBoost model with early stopping. So what do we have? We have the params and we have the BST. In the params, it is interesting to say here that output is the probability of churn, so to say. Eval matrix is good for rare positives, which is in our case, you should know, 1.5. And the tree method is hist, which is fast CPU tree builder. And what else? ETA here is not estimated time of arrival, but it's learning rate. And this is how it looks, the param part. The BST, what is interesting here is the num boost round is 4,000, pretty much the maximum number of small trees. I'll just make it like this, 4,000, so it's visible immediately that it's 4, and then the 1,000. Or I can do it like this. It's better. Yeah, let's leave it. Evals here, says that the validation metric should be watched. This one, DVA. And early stopping grounds is pretty much this one. We'll say that after 200, if it stops improving, then please stop it. So yeah, early stopping watches the validation score and picks the sweet spot automatically. This one, so no guessing. Let's press Shift and Enter and wait. So best number of trees, early stopping chose this 152, which is actually great. And what just happened was XGBoost just built many small decision trees. Each new tree fixes some mistakes made before, but yeah, we are quite okay with 152 trees. If you had to do it manually, you would have probably, I don't know, needed a year, just guessing. But it's good that we're not doing stuff manually anymore. Let's choose the practical decision threshold on validation. Practical decision threshold on validation. Okay, that sounds so nice. I'm going to write it down here as a markdown. Practical decision threshold on validation. And we get a bonus like this, 2 cells hidden. What does it mean, practical decision threshold on validation? Pretty much, this model gives us a probability for each row, whether it's a churn or not. It's between 0 and 1. Let's say for this one, probably without knowing the churn, it can give us 0.73. And for this one, it would give us not exactly 0, it can give us probably 0.41. So what this practical decision threshold on validation means that we should draw a line in the sand to say yes or no. And this line is the best here. Anything above it predicts churn, and below it means no churn. We pick it pretty much by testing many lines and taking the one that gives us the best fit and the best F1 here, F1. And the idea is to balance prediction and recall. Yeah. So let's take a look. And okay, max F1 on validation is 0.446. And let's quickly plot this one just to see how it looks like. Okay, plotting and now waiting. That's bad. POT is not defined. Okay, I'll simply rerun everything because XBoost decided that it wanted to die. Okay. Let me see whether this one is actually remembered. No, of course not. Okay, so I tried to solve it, but I couldn't. So I decided that if I cannot solve it in, let's say, 5 or 7 minutes, then it's probably a better idea just to skip it. What I tried actually is I have reduced the number of pre and rec that I wanted to plot. It didn't work even with 10. Then I saw that the number is really, let's say, the decimals are really up to like a lot of digits after the decimal, and I thought that it can be something to do with the calculation there. So I rounded it up to the second, and it didn't work as well. And I said, okay, I had enough. Let's continue further and test the results with the threshold that we already have. This one, 0446, and this is pretty much when the fun is happening. So let me copy my thing here and I'll paste it for you. Shift and enter. So what we did is a simple confusion matrix with true positive, false positive, true negative, and false negative. So it is BST predict. This is what's happening here. But what you should really be careful about is actually this one here. Confusion matrix and this one. Okay, so here is the true positive. We have 1246, which is okay. And on the other end, we have the true negative that we also care about. Okay, the true negatives are 1246 and the true positive 928. Yes, this diagonal here, like the main diagonal of the matrix, if you have studied linear algebra, these are the good things. Let's say if something is good and we say it's good, if something is bad and our model say it's bad, this is how it should be. The problem is here with the false positive and the false negative. Pretty much what false negative does is it predicted no churn, but it was churn. Yep. And what false negative does is predicted no churn, but it was churn. The other one predicts churn, but it was no churn. Yeah. So it's not good. These both are not okay. Predicted churn and it being no churn is actually okay for our business, I guess, depending on our business ideas. But predicting no churn and it being a churn, then you can get in trouble. Okay, so what is this precision telling us? 0.683. Well, it pretty much says how many times we were correct. Yeah, so this is how many times we were correct, that plus that. And these two are the incorrect. What is the recall telling us? Okay, it's telling us out of all the churners, how many did we catch? And this is actually an interesting thing. It can be that we catch all of them. And it is actually an easy one to catch all of them by just saying everything is a churn. In this case, you will catch all of them, but this is not how machine learning works. Okay. What are these two ROC AUC and PR AUC? So AUC means area under curve, and this ROC AUC of 0.862 actually means that this is the probability that a random positive gets a higher score than a randomly chosen negative, which is, I would say, okay. And this one, PR AUC, is actually the area under the precision recall curve. So the average precision across recall levels as you sweep the threshold with the baseline equal to the positive rate. So far, so good. Let's continue with further analysis. Okay, so this video is over 29 minutes. Good for you for keeping up to now with me. I'll try to speed it up, as I'm pretty sure that a video over 30-35 minutes on machine learning would not be the best thing probably on this channel. But yet, let's continue. So what are we doing here? We have an imp, and this reminds me of Game of Thrones, something about Tyrion Lannister. Let's go with Shift and Enter and see what we got. Actually, it's not Tyrion Lannister, who is actually one of the favorite characters. Almost everyone from Game of Thrones likes him, from the people watching Game of Thrones. So here imp stands for important, and its idea is just to see which one of the 7 unique characteristics of our data actually gives the biggest gain in order to say whether we have churn or not. And in this case, it's support calls. Yes, support calls is actually giving a lot of information on whether we would have a churn or not. So this column matters the most. Yeah, pretty much. Gain actually gives us something interesting. It gives an average error reduction when the model split is on that feature. So bigger is more useful. As I said, 42 is extremely useful. And let's see what do we have here. So top feature, in our case, it would be support calls. And it would pick the number 1 feature, this part of the cell, and see how changing only it shifts the predicted churn on average. So shift and enter. And we actually get something. What does it mean? So we hold all other columns near their meridian, not meridian, but median, and slide only the top feature across a reasonable range. The table shows pretty much the average churn probability the model gives at each feature. And if the number go up, as the feature goes up, the feature raises risk on average. So if they go down, it lowers risk, and if it wiggles, the effect is mixed. So in our case, 0 support calls would be meaning around 8% for churn. And in our case, 8% was no churn. We put the line in the sand on 0.44. So in this case, anything above 7 would be already ringing lamps around and saying, hey, this guy's probably going to churn. Let's not lose the client. Just roughly saying. Okay, so the next one is, just a tiny hint. Let's see what will happen. So there is a trend hint for supporting calls, and it is actually increasing. Happens. What can we do here? In this cell, we do something really nice. We save the model into a UBG file. UBG stands for Universal Binary JSON, and this is a compact representation of text-based JSON format, and it is really used a lot with XGBoost. So if you're gonna work with XGBoost, this is how the model should be saved. Okay, now let's go to the next cell. And in the next cell, pretty much, we are going to add human rules with monotonic constraints. So pretty much here, the idea is that imagine that a manager or a businessman comes and says, what do they say? If the debt ratio, this is one of the characteristics that we care about here, goes up, then the risk should go down, or the risk should not go down, so to say. And if the 10-year months goes up, the risk should not go up. Yeah, and we have the +1 for non-decreasing effect, -1 for non-increasing effect. Okay, shift and enter, and the constraints are coming here, and we just built a new model-based model with 33 new trees, roughly. Okay, does it make sense? It makes sense, at least to us. What we can do now is we can test it versus the old one. We are going to test it versus the old PL AUC and the old LOC AUC. Baseline is the old model, constraint is this one here that we have just done with the constraints. Yeah, shift and enter. And we see pretty much very, very similar data. So our rule following behavior has been done without losing much accuracy. That's good. I mean, depending whether you think that this one is close to this one and this one is close to that one, it can be that, no, I mean, it cannot be closer. Let's put it this way. Yeah. Then what do we say here? Oh, we can do our pre-last cell already, and it is pretty much telling us, let's check the rules and see what is happening. We computed prediction on a clean grid and counted any direction break here. So depth ratio monotonic violations are 0, 10-year monitoring months monotonic violations also 0, which is good. I can make it like that so it's visible that we talk about this. And what is this telling us? It's telling us pretty much the same what that one was telling us. Pretty much with a depth ratio of 10%, we can have a predicted churn of 37.9336, and which is pretty much the same as the one a bit lower. And here you see that the numbers are pretty much matching. Okay. It means that our new rules are perfectly fine. And so far, let's simply delete all the other rows, save the model once more, and make some kind of a overall summary of what has been done so far. Okay, I have something before running everything. I want to import a few new imports. These ones, yes, they are important. Yeah. Average precisions, or actually they are there, so no need. Okay, so shift and enter on everything. We set option for display maximum columns. If you're ever wondering what the 60 is, you can press shift and tap. And you say, okay, display. And it will give you an idea. Display maximum columns is one of the options. And the first parameter is string, value object, new value for option. Okay. I think it's the number of values up to which we see. So any string with more than 60 characters is going to be cut. So this should be it, I guess. Then we put our data frame, we have the shape, the info, and the head, which is nice. The df describe transpose is actually something that everyone should be using, because this way the transposed means something. Then we have the churn value counts. And let's see what happens if we don't have the normalize, just for your idea. We would have the real numbers and they would look like this. But now, without calculating, we know that 5,617 actually stands for 40%. Yeah. Okay, so here the most important thing, we drop the churn column, because without dropping it, it would be pretty much our everything. It would be a spoiler. We are trying to predict how this churn column is actually generated, and it is not. the case, the y here is all the other data from the data frame. Yeah, let's say our two cuts, so to say. First train versus test, and then train validation test. Great. We have negative, positive, and scale positive weight. Means that we have more positive churn than negative, or the other way around, depending on the formula that you are using here. Let's say if the negative are 2 and the positive are 5, then it would be 2 divided by 5, and it would be something like this. And in our case, we have something like that. So it means that we have more negative than positive values. In order to get 1.5, it should be 20, not divided by 10, but something like, no. Okay. What about this? No. I like working with numbers. Yeah, something like this. Yeah, okay, so even 52, 53. So we have, let's say, 53 negatives, for example, and for each 53 negatives, we get 34 positives, 32 positives. What was it, 35? Okay, 36 probably. No, 35 is good. So roughly speaking, we have more negative churn than positive one. Positive churn means we lose the client, negative churn means the client stays with us. Okay, so we are using these feature names for further calculations. This is the first time we have created the model. Then here we have decided that we have to say what is practical decision threshold validation, and it happened. Then here I'll simply say confusion metrics, and I'll make this as a markdown, so it looks nice. Then our confusion metrics says that pretty much the precision, these two, the main diagonal in the matrix, are the precision values. The correct are correct, the wrong are wrong. Here, the non-main diagonal is what we should avoid, but in our case, everything is okay. So the important characteristics that actually work are these ones, and the numbers are changed because I haven't restarted the tool, and some values are currently rewritten, but once you work, make always sure that you restart the kernel correctly. Okay, then the predicted churn looks like this of the support calls. Like the more calls, the bigger the possibility that the client will leave us. Yeah, this is how things work. And the trend for the support calls is increasing. What can we do? We save the model into UBG, which is Universal Binary JSON, which is actually the way the model is saved for XGBoost to use it later. We have put two business logic constraints in our model, pretty much saying that depending on the depth ratio, if it is increasing, then our model should act separately, and when the tenure months, for example, are decreasing, then our model should work differently. Okay, as you see, the numbers here are also changed. Here we have compared the decreasing and the increasing of the two models, pretty much the old one and the one that for which we have our constraints. And we see that we haven't lost a lot. The baseline and the constraint are okay. Then at the end, we make a simple violation analysis. Was there something bad? Is it there something good? Based on our constraint idea here. And at the end, we saved the model. Okay. So far, so good. I really hope that you have stayed with me for what is around 45 or 47 minutes, which is kind of a lot, I guess. And I hope that you have learned something about XGBoost. The Jupyter lab is available in GitHub, and probably I will write an article about it in VitoshAcademy. So, enjoy the rest of your day or night and take care of yourself. Goodbye.